For 14 billion years, the Big Bang has been the ultimate origin story. We all learned that everything that exists exploded from a point smaller than an atom. But what if this is a lie? What if the universe's first moment is not only scientifically impossible and mathematically broken, but simply wrong? Recent discoveries by Nobel Prize winners suggest our universe is just one tiny flickering beat in an infinite, eternal rhythm. The scientific evidence for what came before the Big Bang is now undeniable. If discovery is your thing, subscribe to Stellify Science and turn on notifications so you never miss what the universe reveals next. Our journey into pre-existence begins now, with the paradox that has crippled cosmology for a century. Imagine crushing everything in existence, all matter, all energy, all of space itself, into a space smaller than the period at the end of this sentence. This is the singularity, the supposed starting point of our universe. But here is the massive problem that physicists rarely discuss openly. The mathematics of our best theory completely falls apart at this moment. When you calculate what happened at the very instant of the Big Bang, the equations return infinity. Pattern interrupt. Quick zoom on a mathematical infinity symbol on a black screen. Temperature becomes infinite. Density becomes infinite. And the curvature of space becomes infinite. To a mathematician, infinity is not just a really big number. It's a screaming red flag that something fundamental has gone wrong with the theory. General relativity, Einstein's masterpiece that describes gravity and the shape of space, works brilliantly almost everywhere in the universe. It predicts black holes and explains why GPS satellites need time corrections. But at the singularity, general relativity breaks down completely. The theory that explains everything suddenly explains nothing. This is what physicists call the singularity problem. If our best theory of gravity cannot describe the most important moment in cosmic history, then we are missing something crucial. Stephen Hawking spent decades wrestling with this puzzle. Roger Penrose won a Nobel Prize partly for proving that singularities are mathematically inevitable in Einstein's theory. Both men eventually concluded something radical. Maybe the singularity never actually existed. Every atom in your body, every star in the sky, supposedly exploded from a mathematical impossibility. The entire universe emerged from a point where the laws of physics themselves cannot operate. The problem gets worse when you add quantum mechanics to the mix. Quantum physics describes the behavior of tiny particles, and at the incredibly small scales of the singularity, quantum effects should dominate. Yet, we do not have a working theory that combines quantum mechanics with gravity. We are literally blind to what happened at the most critical instant. Some physicists argue we should just accept the singularity as the beginning of time itself. Before that moment, there was no before. But this explanation feels like giving up. It is like a detective declaring the criminal simply appeared from nowhere. Others suggest we need a quantum theory of gravity to truly see what happened. Over the past 20 years, several such theories have emerged, and they reveal something extraordinary. The singularity might be an illusion. Instead of a beginning from nothing, these theories predict something existed before. Our universe might not be the first act in cosmic history. It might be the sequel. What if the Big Bang was not a beginning, but a transition? Roger Penrose is not one to make wild claims lightly. At 94 years old, he concluded the universe is not a one-time event. It goes through infinite cycles. Each cycle begins with what we call a Big Bang and ends in a strange far future state. The remarkable part is that the ending of one cycle becomes the beginning of the next. Our universe, according to this conformal cyclic cosmology theory, is just one chapter in an eternal book. This is a Nobel laureate saying that everything you learned about cosmic origins might be wrong. Penrose's idea is different from other speculative theories because it makes predictions we can actually test. He claims that violent events from the previous universe should have left marks on our universe. Specifically, he looked for unusual patterns in the faint glow of radiation that fills all of space, the cosmic microwave background, or CMB. This CMB glow is like a baby photo of the universe, showing us what conditions were like 380,000 years after the Big Bang. Penrose and his collaborators analyzed data from satellites that map this radiation, and they claim to find exactly what the theory predicted. Circles of abnormal temperature, which they called Hawking points. These Hawking points, according to Penrose, are the final evaporations of supermassive black holes from the universe before ours. The radiation from those ancient black holes supposedly survived the transition and appears as hotspots in our sky. We'll dive deeper into this evidence in a moment. But first, let's understand the mind-bending math that makes this cosmic inheritance possible. To understand how one universe could become another, you need to grasp a strange property of space and time called conformal geometry. This is a branch of mathematics that studies angles and light paths while ignoring absolute sizes. Here is why that matters for cosmology. Imagine the universe in the distant future, trillions upon trillions of years from now. All stars have burned out. All matter has decayed or fallen into black holes. Those black holes themselves have evaporated through Hawking radiation. What remains is nearly empty space filled only with photons, massless particles of light, racing away from each other as the universe expands. In this remote future, nothing has mass anymore. Particles with mass experience time. They age. But a massless photon does not experience time in the same way. For a photon, the journey from one end of the universe to another happens instantly from its own perspective. When the universe reaches this state of pure radiation, with no massive particles, the concept of size becomes meaningless. If you have no rulers made of atoms, no clocks made of matter, no reference points with mass, then you cannot measure distances or duration. The universe effectively loses track of its own scale. Penrose realized you could take this far future universe and mathematically transform it. Using conformal geometry, you can rescale it, so the infinite expanse of the dying universe becomes the infinitely small point of a new Big Bang. The ending and the beginning are the same event, viewed from different perspectives. This is not arbitrary. This transformation preserves the geometry that matters for light and radiation. Information encoded in light could theoretically survive the transition. The new universe does not start from nothing. It inherits structure from its predecessor. This rescaling solves two deep problems in standard cosmology. First, the entropy problem. Why did the universe start in such a special, low entropy, incredibly ordered state? Penrose's cycles provide an answer. The order comes from the smooth, empty state at the end of the previous cycle. The far future naturally produces the low entropy conditions needed for a new beginning. Second, the uniformity of our universe. Why does the CMB look nearly identical in every direction? In CCC, uniformity emerges naturally from the previous cycle. The long period of expansion in the old universe smooths everything out. When that smooth ending becomes the new beginning, the uniformity carries over. No inflation needed, and no special initial conditions required. But what about the evidence? Penrose's claim to have found actual remnants of a previous universe launched one of the most heated debates in modern science.
And yet here it is.
The theory
doing all of
predicts
that.
that supermassive black holes from the previous universe would eventually evaporate through Hawking radiation over an incomprehensible amount of time, 100 years. When the conformal rescaling happens, turning that far future into our Big Bang, these final bursts of energy would leave imprints. They would appear as specific types of anomalies in our cosmic microwave background. Penrose predicted these imprints would look like circular regions where the temperature falls off in a characteristic way from a central hotspot. The circles would have diameters about 5 times the width of the full moon in our sky. In 2010, Penrose and his collaborator, Vahe Gurzadyan, claimed they found exactly these patterns, identifying numerous concentric circles. They calculated that the probability of seeing so many such circles by random chance was extremely small, less than 1 in a billion. The announcement created immediate controversy. Multiple research teams rushed to check the findings, and within months, 3 independent groups published rebuttals. They analyzed the same data and found no unusual excess of circles. They argued that even simulated universes, based on standard cosmology, produce just as many circular patterns as the real data. The disagreement came down to methodology and statistics. How do you decide what counts as a significant circle? Undeterred, Penrose refined his approach. In 2018, he published a new analysis, this time searching for concentrated hotspots rather than circles. He found patches in the CMB that were significantly hotter than surrounding regions. The temperature differences were about 10 times larger than the cosmic average, far beyond what his team's simulated universes could produce. He argued these hotspots were exactly what you would expect from Hawking points, where a black hole's final evaporation injected enormous energy into a small region. Again, the broader community remained skeptical. Critics noted that if you search for enough different patterns in noisy data, you will eventually find something that looks special by chance alone. As of now, the existence of Hawking points remains unproven. The evidence is highly disputed. But regardless of whether Penrose is right or wrong, his brilliant mind looked at the universe and opened a door that many thought was permanently sealed. The door to what existed before. The search for the Big Bang's predecessor led us to an even deeper mystery: the universe's inexplicable initial order. The second law of thermodynamics states that entropy always increases. Your room gets messy unless you actively clean it. Stars eventually burn out. Everything tends toward disorder. Yet, the Big Bang apparently started in an incredibly ordered state. When we look at the cosmic microwave background, we see an almost perfectly smooth universe. Temperature variations are only 1 part in 100,000. This extraordinary smoothness represents extremely low entropy. Where did that order come from? In statistical mechanics, low entropy states are spectacularly improbable. Imagine throwing a deck of cards into the air. The probability that they land in perfect numerical order is essentially 0. Now, imagine a deck containing 10^10 particles. The odds of them starting in such an organized configuration are incomprehensibly small. Standard Big Bang cosmology does not explain this initial order. It simply assumes the universe started that way. This assumption is called the past hypothesis, and it's a profound restatement of the puzzle. Roger Penrose calculated just how special the initial state actually was. He estimated that the gravitational degrees of freedom at the Big Bang were tuned to a precision of 1 part, in 10 to the power of 10 to the power of 123. Let that number sink in. It's a 10 with 123 zeros after it, and then you take 10 to that power. Writing it out would require more digits than there are atoms in the observable universe. The universe started in an absurdly improbable state. Cosmic inflation provides one answer, suggesting a brief period of faster-than-light expansion smoothed out irregularities, like stretching a wrinkled bedsheet. But conformal cyclic cosmology provides an alternative. The order comes from cosmic recycling. The far future of the old universe naturally becomes smooth. And when that smooth ending transitions into a new beginning, the low entropy simply carries over. The past hypothesis is not an assumption. It's a consequence of the universe's eternal rhythm. This creates a new question. What about the entropy from the old universe? If entropy always increases, shouldn't each cycle become more disordered than the last? This entropy problem in cyclic cosmology remains controversial, but another competing theory offers a dramatic solution that doesn't rely on Penrose's mathematical tricks. Deep beneath the smooth appearance of space lies a profound truth about reality's nature. Most people think of space as just emptiness, but quantum physics suggests reality is more complex. Even the vacuum of space has structure, and that structure might save the universe from the singularity problem. Loop quantum gravity, LQG, is one of the leading approaches to merging quantum mechanics with Einstein's general relativity. It starts with a radical idea. Space itself is not infinitely divisible. You cannot keep zooming into smaller and smaller distances forever. Eventually, you hit a fundamental limit called the Planck length, about 10^35 meters. At this scale, space is not continuous. It is granular, made of discrete quantum units, like pixels on a screen. LQG describes gravity not as the curvature of smooth space, but as dynamic loops of gravitational field that weave together to form the fabric of spacetime. This picture changes everything about singularities. In classical general relativity, matter collapses to infinite density. But in loop quantum gravity, infinite compression is impossible. You cannot squeeze below the Planck scale, because there is no space smaller than a Planck length. As matter collapses and density grows, quantum effects become stronger. When the density reaches the Planck density, about 10^9 grams per cubic centimeter, something dramatic happens. Gravity itself becomes repulsive. The collapsing matter bounces back outward. Instead of a singularity, you get a big bounce. This prediction led to loop quantum cosmology, which showed that the universe does not begin from an infinitely compressed point. It rebounds from a previous contracting phase. Imagine running cosmic history backward. Galaxies get closer together, and the universe gets smaller and denser. In standard cosmology, you hit the singularity, and your equations break. In LQG, as you approach the Planck density, quantum repulsion takes over. The contraction reverses into expansion. Detailed simulations confirm this behavior, smoothly connecting a contracting phase to an expanding phase. Crucially, some information from the contracting phase survives the bounce. This means we could potentially learn about the pre-bounce universe by studying our current universe's properties, like the cosmic microwave background. Loop quantum cosmology also solves the horizon problem. How distant regions of the universe, which have never communicated with each other, ended up with nearly identical properties. During the contracting phase before the bounce, regions that are now far apart were once in contact. They came to equilibrium back then, and when the universe bounced, that equilibrium was preserved. No inflation needed. The Big Bounce hypothesis comes in several versions, but they share the core elements. Our universe was preceded by a contracting phase, and instead of forming a singularity, quantum effects intervened, halting the collapse and reversing it into expansion. The universe did not begin. It changed form. This shift in perspective is as profound as the Copernican revolution. We are not witnessing the beginning of existence. We are watching one phase in an ongoing process. What happened in the contracting universe before the bounce? Here, the evidence becomes speculative. Some models suggest the previous universe was similar to ours, just running in reverse time. Others propose the contracting phase had very different properties. The matter content, the geometry, even the constants of nature might have differed. One intriguing possibility is that information could survive the bounce. The scalar fields representing matter and energy evolve continuously, creating what physicists call a quantum bridge. This bridge connects the two phases without ever reaching zero volume. If information survives, then relics from the pre-bounce universe could exist in ours, not as physical objects, but as subtle correlations in the quantum fields. Calculations show that the wave function, the mathematical object describing the quantum state of the universe, smoothly passes through the region of minimum volume and emerges on the other side, corresponding to an expanding universe. The quantum bridge itself lasts for the briefest instant, roughly 1 Planck time, about 10 to 43 seconds. The quantum bridge ensures that the universe is not fragmented into disconnected epochs. Past, present, and future are linked by continuous quantum evolution. The bounce is not a wall blocking our knowledge. It is a gateway, admittedly narrow and obscure, but a gateway nonetheless. The Big Bounce, however, is not the only alternative to the Big Bang. String theory, the leading candidate for a theory of everything, introduces the possibility of extra dimensions and another bizarre cyclic model. String theory requires more than the 4 dimensions we observe. It needs 6 additional spatial dimensions, making space 10-dimensional total. These extra dimensions are not missing. They are curled up so small we cannot detect them. Imagine a garden hose viewed from far away. It looks like a one-dimensional line, but up close, you see it has thickness, with a circular dimension wrapped around the length. These hidden dimensions profoundly affect physics. The size and shape of the extra dimensions determine the properties of particles and forces in the visible dimensions. String theorists estimate there are roughly 2,510 possible configurations of these extra dimensions, creating a vast landscape of possibilities. The extra dimensions also allow for extended objects larger than one-dimensional strings. A two-dimensional surface extending through space is called a membrane, or brane. Our familiar three-dimensional space might actually be a three-brane, a sheet embedded in the higher dimensional space called the bulk. This brane world picture led to the ekpyrotic scenario proposed by Paul Steinhardt and Neil Turok in 2001. This model suggests our universe is a three-brane floating in a higher dimensional bulk. Nearby, separated by a gap across an extra dimension, floats another parallel brane. These two branes are attracted to each other by gravitational forces acting through the bulk. Occasionally, the branes collide. When they crash together, the collision releases enormous energy, which appears as hot matter and radiation on the branes. From the perspective of anyone on the brane, this looks exactly like a Big Bang. But it is not the beginning of space or time. It is just a collision event in an ongoing history. After the collision, the branes bounce apart, move back through the bulk, slow down, and eventually start approaching again. The cycle repeats endlessly. Each collision is a new Big Bang. The ekpyrotic scenario has several advantages. It naturally explains why the universe started in a smooth, flat state. The slow approach of the branes before the collision allows quantum fluctuations to create uniform patterns. No inflation needed. It also addresses the entropy problem. Each cycle adds entropy, but the expansion between collisions provides more space, allowing the cycle to repeat without violating the second law of thermodynamics. The key test for the ekpyrotic model is its prediction about primordial gravitational waves. During the collision, the brains generate density perturbations, but very few gravitational waves. This is the opposite of the leading alternative, inflation, which produces substantial gravitational waves. We'll discuss how we're testing this difference in a moment. The problem, however, is that even describing the Big Bang as a brain collision doesn't automatically avoid singularities. At the moment of collision, energy densities and temperatures become infinite within the standard mathematical framework. Proponents argue that string theory, when fully understood, will resolve this, but the singularity remains a problematic gap. Despite the challenges, the idea of vast structures in higher dimensions producing our reality as a side effect is a humbling idea. Our universe is simply an impact in an ongoing story. The ancient Stoic philosophers imagined a universe born from fire, destroyed by fire, and reborn from fire again in an endless cycle. Modern ekpyrotic theory translates this ancient intuition into a rigorous, testable, string theory-based model. If the big bounce and the brain collision models suggest an eternal, singular universe, the most successful current theory of the early universe suggests an entirely different, infinite scenario. Cosmic inflation, originally designed to solve a technical problem called the monopole problem, inadvertently implied our universe is just one bubble in an infinite foam. Inflation posits that right after the Big Bang, the universe underwent a brief period of faster-than-light expansion driven by a field called the inflaton. This rapid growth smoothed out irregularities and flattened the geometry, solving several major cosmological puzzles. Inflation quickly became the leading theory of the early universe, but as physicists explored mathematics more deeply, they discovered something unexpected. Inflation does not just happen once and stop everywhere at the same time. In most versions of the theory, inflation is eternal. The process works like this. The inflaton field drives expansion when its energy density is high. As the field gradually decays, inflation stops in that region, and a hot Big Bang begins. That region becomes a pocket universe like ours. But space is expanding exponentially. Even though inflation ends in some places, the expanding regions between those places grow faster than the non-inflating regions can fill them. New volume is created faster than old volume can convert. The total amount of inflating space increases without limit, spawning more and more pocket universes forever. Andre Lin, one of the pioneers of inflation theory, proved that eternal inflation is generic. Almost any inflation model leads to it. Alan Guth famously said, "It is hard to build models of inflation that do not lead to a multiverse." The multiverse arising from eternal inflation is vast beyond comprehension. It is infinite. Every possible way that inflation could end happens infinitely many times in different places. Every possible set of physical constants that could emerge appears somewhere. This leads to the ultimate paradox of cosmology, the measure problem. In an infinite multiverse, everything that can happen does happen. There are infinite copies of Earth, infinite copies of you, and infinite universes. With completely different physics, how do you calculate probabilities? Normally, probability means counting favorable outcomes divided by total outcomes. But if there are infinite favorable outcomes and infinite total outcomes, you get infinity divided by infinity, which is undefined. Mathematics breaks down. The predictions of eternal inflation depend on how you order your counting procedure which seems arbitrary. The theories that predict everything are actually predicting nothing. This forces cosmologists to use philosophical reasoning. Why is our universe so finely tuned for life? Because we exist. Universes with large vacuum energy do not form stable galaxies and stars. We live in a rare pocket with physics that allows observers. This is called the anthropic principle, and it is a deeply unsatisfying answer for many physicists. The measure problem indicates that multiverse theories are not scientific in the traditional sense, as they cannot be falsified. Any observation is compatible with the theory. This unresolved issue is why many physicists resist multiverse theories despite the theoretical motivations for them. But the eternal inflation model brings with it another disturbing possibility, one that underpins the nature of our local Big Bang: the false vacuum. Empty space is not as empty as it seems. Quantum field theory reveals that what we call a vacuum is teeming with activity, and it can exist in different states, like water existing as ice or liquid. The lowest energy state is the true vacuum. Higher energy states are called false vacuums. If the universe is currently in a false vacuum, it could potentially decay into a lower energy state with dramatic consequences. False vacuum decay was first analyzed in the 1970s. The process begins with a random quantum fluctuation that creates a tiny bubble of true vacuum. This bubble has lower energy than the surrounding false vacuum, and the energy difference creates pressure that causes the bubble wall to expand at nearly the speed of light. Inside the bubble, the laws of physics might be completely different. False vacuum decay provides the mechanism for eternal inflation. Our universe is such a pocket. Inflation ended here about 13.8 billion years ago, when the local patch of false vacuum decayed. The energy released during that decay became the matter and radiation in our pocket. That was our Big Bang. But could we still be in a false vacuum? Could our current universe be metastable, capable of decaying to an even lower energy state? Calculations suggest this is possible. The measured masses of the Higgs boson and the top quark place our universe near the boundary between stability and metastability. If we are in a false vacuum, decay could happen at any moment. A bubble of true vacuum could nucleate anywhere in space tomorrow. Once formed, it would expand at light speed. We would have no warning. The bubble wall would arrive without announcement, erasing everything we know. Fortunately, calculations indicate such a decay is extraordinarily unlikely on human timescales. The universe could persist in its current state, for durations vastly exceeding its current age. Still, the idea that reality itself could collapse at any instant remains disturbing. The false vacuum is both a trap and a gateway. It traps us in a temporary island of stability, but it also serves as the gateway through which new universes are born. All of these theories, the Big Bounce, cyclic cosmology, and eternal inflation, make specific predictions about what we should be able to observe. The ultimate tiebreaker lies in a signature invisible to our eyes: primordial gravitational waves. Gravitational waves are ripples in space-time. Primordial gravitational waves are fossils from the universe's birth, created by quantum fluctuations when the universe was unimaginably small and hot. They pervade all of space, a background hum from the beginning of time. Different theories of the early universe predict vastly different gravitational wave signatures, making them the most powerful tool for testing what came before the Big Bang. The leading theory, inflation, generates gravitational waves through a specific mechanism. During the exponential expansion, quantum jitter in the gravitational field gets amplified, becoming classical gravitational waves. The wave strength, or tensor power spectrum, depends on how fast space expanded. High-energy inflation produces strong waves. Conversely, cyclic cosmologies predict much weaker gravitational waves. During the contracting phase before the bounce, gravitational perturbations do not get amplified as much. The ekpyrotic model, in particular, predicts extremely weak or absent waves. Loop quantum cosmology predicts moderate signals, often in a different frequency range. How do we detect these ancient, faint ripples? They leave imprints on the cosmic microwave background. The waves create a specific polarization pattern in the ancient light called B-mode polarization. Detecting B-modes would be the first evidence of primordial gravitational waves. Several experiments have searched for B-modes. In 2014, the BICEP-2 telescope claimed a detection, causing enormous excitement, as it would confirm high-energy inflation and rule out many alternatives. However, further analysis showed the signal came from dust in our galaxy, not from primordial waves. The search continues with improved experiments. The next decade will be decisive. Space-based gravitational wave detectors like LISA will open new windows, sensitive to lower frequencies than ground-based instruments. Pulsar timing arrays, which monitor neutron stars, offer another detection method for extremely long wavelength waves. If any of these experiments detect primordial gravitational waves with high confidence, we learn about the energy scale of the early universe. Strong waves favor high energy inflation and the multiverse. Weak or absent waves favor cyclic and bouncing models. The universe is about to tell us its oldest secret. The more we explore these models, the more we realize that the central problem of cosmology might be a flaw in our intuition. What if time never started? What if the universe has always existed, stretching infinitely into the past with no first moment? This idea violates our intuition. Everything we experience has a beginning, but the equations do not require a beginning. Several cosmological models suggest time is eternal in both directions. For instance, loop quantum cosmology, with infinite bounces, suggests the universe has always been bouncing, with no first bounce. Conformal cyclic cosmology makes a similar claim. Penrose's cycles stretch to infinity in the past, with no first eon. The infinite regress never terminates. Our eon is one beat in an eternal rhythm. Even the time-symmetric Big Bang models, like those explored by Alan Guth and Sean Carroll, suggest our Big Bang is just a moment of minimum entropy. On one side, entropy increases. On the other side, entropy also increases. But time flows in the opposite direction from our perspective. The universe is symmetric in time, and neither side is the true beginning. Philosophically, time without a beginning challenges deep intuitions. Humans naturally ask, what came first? But mathematically, eternal time is perfectly acceptable. The biggest challenge for these models is explaining the low entropy state we observe today. If time is eternal, an infinite past should have infinite opportunities for entropy to increase. The universe should be in a maximum disorder, yet we observe high order. This is the Boltzmann brain problem, which suggests either time is not truly eternal, or our understanding of probability in infinite systems is fundamentally flawed. Ultimately, the question of what came before requires looking at converging lines of evidence. If gravitational waves, microwave background patterns, galaxy distributions, and particle physics observations all point the same direction, the case becomes compelling. The next 2 decades will likely settle the question. Current experiments have the sensitivity to detect predicted signals. and future upgrades will push even further. By mid-century, cosmology might finally know whether the Big Bang was the beginning of time or merely one event in an eternal cosmic history. We stand at the threshold. The telescopes are being built. The detectors are coming online. We are not witnessing the dawn of existence. We are watching one phase in an ongoing, possibly eternal process. If this changed how you see the ultimate origin story, watch this next on the Truth About the Black Hole Information Paradox. To keep the story going and understand where the information from a previous universe might hide.